Hello, Physics 20s. In today's lesson, we're going to talk about inclined planes, and specifically, we're going to apply Newton's laws of motion to solve algebraically linear motion problems on inclined planes near the surface of the Earth, ignoring air resistance. Let's start off with a situation where we have an object on an inclined plane that is being pulled down the incline. What I want to do is I want to draw a free body and mass acceleration diagram of the object on the inclined plane. If I draw a free body diagram of the object on the incline, so again, you can kind of envision the scenario like this. So we have our incline, and we have our object, a box on the inclined plane, and we're just going to pull it straight down the incline. Well, we'd have the force of gravity that's straight down towards the center of the Earth. We'd have a normal force acting on the object, which is both perpendicular to the ground and points towards my object. We'd have an applied force that is down the ramp, and we'd have the force of friction, which is up the ramp, opposing the direction of motion. The assumption I'm making right here is this object is actually moving. Therefore, if I drew a mass acceleration diagram, I would identify that the acceleration is down the incline. Now, if I were to look at the equations of motion for this object in both the x and y direction, this would be a nightmare. The reason being is if I looked at the sum of the forces in the x direction and the sum of the forces in the y direction, there are a lot of forces you would have to break into x and y components. You would have to break the applied force into x and y components. You'd have to break the normal force into x and y components. You'd have to break the force of friction into x and y components. And you'd also have to break the acceleration into x and y components. So of the 5 vectors I can see from the free body and mass acceleration diagram, if we took our standard approach of dealing with the horizontal and vertical planes, we'd have to break 4 of those 5 vectors into x and y components. That would make it a nightmare to deal with the equations of motion. So what we don't want is we don't want to use equations of motion that are going to be in the horizontal and vertical plane. What we want to do is we want to use a different axis, an axis that better lines up with the actual incline. And here's what I mean by this. In all of our problems so far, we've dealt with equations of motion that were either in the x direction or the y direction. And if we had a force in an angle, we broke it into x and y components. Again, we don't want to do this right now because we'd have to break 4 vectors into x and y components. So what we can do is we can take this axis and we can rotate it to an axis that's a bit easier to deal with. So on the picture here, I showed that the dashed line represents the standard y and x axis. And what you want to do is you want to take the axis and you want to rotate it so that the x-axis is lined up with the angle of the incline, like it lines up with the direction the incline points. This double line right here, this means an axis that is parallel to the inclined plane. This symbol, I'm going to add a little square at the top there, means that this axis is perpendicular to the incline. Now, if we ask that same question again, if I use my rotated axis, and how many of these force vectors would I then need to break in components? Well, the normal force is in the perpendicular direction, the force of friction, the force applied, and the acceleration are in the parallel direction. The only vector that does not line up with the perpendicular or parallel axis is the force of gravity. But this is a lot better. We're only going to have to worry about breaking 1 vector into components as opposed to 4. So let's deal with this force of gravity. What we want to do is break it into two components. One component where we have the force of gravity parallel to the incline, and one component where it is perpendicular to the incline. So here's one force of gravity vector that points straight down. I'm going to draw two vector components that represent a component of the force of gravity that is perpendicular to the incline. So that's this one. Again, I'll add a little square here for perpendicular. FG perpendicular. And you have a component on the bottom that would be parallel. All I want to do right now is I want to just simply determine an equation I can use to calculate the perpendicular component and parallel component if I know what the angle is and also what the force of gravity is. And I should point out this angle theta that's at the very top of the triangle, this is the angle of the incline. In the example problem, I'll in a sense show you like why it is this angle, but that is the angle of the incline. Okay, so let's look at this. FG perpendicular compared to the angle theta is your side adjacent. If you know what the hypotenuse is, the way I could calculate the perpendicular component of the force of gravity would be take the force of gravity magnitude and multiply by cosine theta. I could actually drop the absolute value vector and just write it like FG perpendicular would be equal to FG times cosine theta. The parallel component is on the opposite side of the angle theta. So if I take opposite over my hypotenuse, that'd be the sine ratio. Therefore, if I want to calculate the parallel component, FG parallel, it would be equal to the force of gravity multiplied by cosine of theta. So I only have one force vector I need to break into perpendicular and parallel components. All right, so example. I have a 40 kilogram box. It's being accelerated up an incline that makes an angle of 35.0 degrees with the horizontal by an applied force of 300 newtons, parallel to the incline. I'm told the coefficient of kinetic friction between the block and the incline, and I want to calculate the magnitude of the normal force acting on the block, determine the acceleration of the block, and I want to figure out the net force on the block. So first things first, I'm just going to show my rotated axis. My rotated axis, this top axis right here would be the perpendicular axis to the incline. This bottom one would be the parallel axis to the incline. I'm going to start off by drawing a free body diagram of the object on the incline. So let's go to an FBD. What I'm going to do is I'm going to heavily exaggerate the angle of the incline. I'm going to make it really small. Now, on a free body diagram, you're not supposed to show the object, the other objects that your object of interest is in contact in. So I'm not supposed to show the actual incline, but I'll do a line right here just to represent it for the time being. And then maybe later on I'll erase it. And actually, maybe right now I'll just do it in a different ink color. So I'm going to heavily exaggerate the angle. I'm going to make it really small. Theta. And I'll also do it for the mass acceleration diagram, which I'm going to deal with in a moment. Now, I've drawn that in blue because technically, again, on a free body diagram, you're not supposed to show other surfaces or objects that your main object of interest is in contact with. Okay, so let's draw the blocks now. May as well do the mass acceleration diagram first because it's a lot easier. I have a mass, and we're pushing this thing up the incline, so my acceleration is going to be up the inclined plane. Now, on the free body diagram, let's draw all of our forces. So first things first, let's deal with this force of gravity. So I'll make it really big just to exaggerate it. So we have Fg. That would be straight down. And I'm going to draw the components of the force of gravity with a different color. This time I'll pick purple. So I need to form a right angle triangle. So I'll draw my perpendicular component first. So this would be Fg, perpendicular, and then parallel component, form this right angle triangle, would be Fg parallel. Now, the reason I heavily exaggerated the angle of the incline, like I made it really, really small, is because it should make it clear which angle in the components diagram is the angle theta. So on the components diagram, there's two angles. There's this one angle at the bottom. I'm assuming you can see the mouse clicker. And you have this angle at the top. Now, I made the angle of the incline tiny. So let's compare to this components diagram. I have an angle down here, an angle at the bottom. Sorry, angle down here, an angle at the top. The angle of the incline is the tiny one. So if I look at my components diagram, which angle is the small one? This bottom one or the top one? Well, it's the top one. So the top one is going to be the angle theta. That's the smaller angle. Let's draw the rest of the forces on the free body diagram. So we would have a normal force that is perpendicular to my object. Sorry, perpendicular to the surface and points towards my object, so Fn. We would have an applied force that is up the incline. We'll call that Fa. And then we have the force of friction, which would be parallel to the incline. And we have Ff. Okay, so that's my completely labeled free body mass acceleration diagram. The first part of the question wants me to figure out the normal force. I'm going to use my rotated axis to write down my equations of motion. So my rotated axis, we're going to sum forces on the perpendicular axis and the parallel axis. The normal force is a force along the perpendicular axis, so that's where we're going to start. So let's say that up and a little bit towards the right is positive, and I'm going to find the sum of my forces acting on the object in the perpendicular direction. Now, if you look at the mass acceleration diagram, there is no motion in the perpendicular direction. All motion and acceleration is in the parallel direction, which means my forces are balanced. Specifically, if you look at the free body diagram, it's the normal force that is being balanced by the perpendicular component of the object's weight. So this little perpendicular vector here is being perfectly offset by the normal force. So I'd say the sum of the forces is equal to 0, which tells me I'm dealing with the balanced forces physics principle. If we expand the equation of motion, okay, so if it's up and right, it's positive. If it's down and left, it's going to be negative. Therefore, Fn would be positive. So you have positive Fn. Subtract Fg, perpendicular, will be equal to 0. If we expand the equation of motion, it'd be Fn. Subtract Fg perpendicular is Fg. Multiply by, we'll look at your components diagram. The perpendicular component is on the adjacent side, so we'll use the cosine ratio. Cosine theta And let's expand this a little bit upward. So this would become Fn, subtract, Fg is just m times g, so you'd have mg cosine theta, and that is equal to 0. If we isolate for Fn, it would be Fn is equal to mg cosine theta. All I have to do now is plug numbers in. So we go Fn would be equal to your mass, which is 40.0 kilograms, multiplied by 9.81 meters per second squared, multiplied by cosine of the angle, which is 35.0 degrees. And then the normal force that I calculated to 3 significant digits would be 321 newtons. Let's box that answer. That's the magnitude of the normal force. Okay, that's part A. Now, part B wants us to figure out the acceleration of the box. The acceleration of the block is going to be in the parallel direction. So maybe let's just take a quick look before we go to the next slide and start writing the equation of motion. In the parallel direction, I have 3 forces. I have the applied force, which would be up the ramp. I have the force of friction, which is down the ramp. And I also have the parallel component of the object's weight, which is down the ramp. So let's go to writing the second equation of motion. Just ignore the assignment for now. I meant to put an extra slide in here with the example continued, but I forgot to put it in. Okay, let's say that down the incline is positive. Now I'm going to find the sum of my forces in the parallel direction is equal to mass times acceleration in the parallel direction. Because we have acceleration, that tells me that the forces are unbalanced. So this means, look at the free body diagram, look at the forces in the parallel direction. If the vector points down the incline, it's positive. Up the incline is going to be negative. So let's go back for a moment. FF is down the incline, it's positive. FG parallel is down the incline, positive. FA is up the incline, negative. And your acceleration is up the incline, so it would also be a negative. Let's go back here and expand the equation of motion. So this would then become, let's write down the positive forces first. So we would have force of friction, so it's positive because it's down the incline, plus the parallel component of my weight, subtract the applied force, and that would be equal to mass times the acceleration. The acceleration is up the incline, so that would be negative according to this notation. Let's expand this. We're talking about kinetic friction. So the kinetic friction would be equal to the coefficient of kinetic friction, mu k, multiplied by your normal force, plus Fg parallel would be Fg times sine of theta. We can see this from the components diagram. On the components diagram, relative to the angle theta, Fg parallel is the opposite side. So we're going to use a sine ratio. Subtract Fa. And that would be equal to negative m times a. Okay, let's expand this equation a little bit more. So we'd have mu k times Fn plus Fg is m times g, mg sine theta, minus Fa is equal to negative m times a. We need to solve for the system acceleration. Now, I could divide both sides of the equation by negative m and just solve it, but it just looks kind of messy. So I think just to make the equation a little bit better in terms of negatives, I'm just going to take the entire equation and multiply both sides by -1. This would be equivalent to just taking all the terms and just moving them to the other side of the equation. So if I did that, this would then become, let's write the positive term first. Now, FA would be positive, so you'd have FA subtract mu k Fn minus mg sine theta would be equal to m times a. To get the a by itself, just divide both sides of the equation by the m. So you'd have a would then be equal to Fa subtract mu k Fn minus mg sine theta, all divided by the mass. Now we can plug numbers into the equation. All right, so Fa is 300 newtons. Mu k is 0.100. The normal force, we'll use the rounded answer from part A, which was 321 newtons. Subtract m, which is 40.0 kilograms, times the magnitude of the acceleration due to gravity, 9.81 meters per second squared, multiplied by sine of that angle, which is 35.0 degrees. And then divide this all by the mass. Divide by 40.0 kilograms. Let's put the top in its own set of brackets so we don't mess the order of operations up. And then when we calculate this acceleration magnitude to 3 significant digits, I get 1.07 meters per second squared. Part C wants me to figure out what is the magnitude of the net force on the block. Now, there are two ways you can do this. One way would be a little bit more work. One way would be a little bit less work. So I'll kind of highlight to you both ways you can do this. So we've got part C. Okay, if we look at our acceleration equation at the top, that acceleration equation is just, it's put in a format where you have acceleration is just equal to the net force divided by m, okay? A matches up with A, M matches up with M, therefore the numerator needs to be the net force. So one way I could do it is I could just plug all numbers into the numerator and calculate the net force. But there's an easier way to do it. As soon as you know what the acceleration is, we can just use Newton's second law to figure out the net force, because Newton's second law tells us the net force acting on an object is equal to mass times the acceleration of the object. So all we need to do is take that acceleration and multiply by the mass. Well, let's drop the vector signs because we're dealing just with magnitude. So to have the net force. Now the net force is only in the parallel direction, so let's add the little parallel symbol. And that'd be mass times acceleration in the parallel direction. Plug numbers in now. The mass is 40.0 kilograms. The acceleration is 1.07 meters per second squared. And then I would get the magnitude of this net force, which is only in the parallel direction. Again, the perpendicular direction the forces are balanced would be, I get 42.8 newtons. And that's it. So when dealing with an inclined plane, as long as you rotate the axis, it'll make our calculations much, much easier. And that is the exact problem-solving strategy we want to use. Otherwise, it's just business as usual, where we mathematically model the situation by drawing free body mass acceleration diagrams and then writing and expanding equations of motion. So in the meantime, you need to complete the assignment called Inclined Planes, and I'll talk to you next time in the final lecture for dynamics on Newton's third law of motion.